For the last several days, week or so actually, we've been looking at energy, kinetic energy, potential energy, work, power, conservation of energy. I want to kind of focus on a couple of those topics right now as part of a review here. Work and conservation of energy. We defined work here last week as the change in energy experienced by the object, the gain or loss of energy experienced by the object. So W essentially became delta E. We also call that the work energy theorem, right? Telling us that change in energy is equal to work. Now, conservation of energy, when we state it mathematically, says that the total energy at the beginning of the problem is equal to the total energy at the end of the problem. In other words, EI is equal to EF. Look, if W is delta E and delta E is EF minus EI, then how can you possibly have work done on an object? How can you possibly have a change in energy of an object when the initial energy is equal to the final energy? By this rationale, shouldn't EF minus EI always be equal to 0? When we're talking about work, if you go back to that for a second, okay, the couple of days when we were dealing with work and power, what we were always talking about there was a specific kind of energy or the energy of an individual object. Look, right now, I have no energy. Right now, as I move across the room, I have kinetic energy. Created energy, right? No, I didn't create energy from nothing. There was work done on me, work done by my legs on my body. But in the end, it still wasn't it still essentially was just a conversion of chemical potential energy in my body to kinetic energy as I'm walking across the floor. Basically, when we're dealing with work, we're dealing with the change in one kind of energy. I gained kinetic energy as I walked across the floor. I didn't pay any attention to the chemical potential energy that I lost. I gained kinetic energy. When we talk about conservation of energy, EI is equal to EF, we're looking at bigger picture. We're looking at all the kinds of energy. We're accounting for everything. And when we account for everything, there isn't a change in energy. The total amount of energy remains the same. So when we're looking at one small part of it, things can gain energy and lose energy. When we're looking at bigger picture, everything, all the energy involved, then EI will always be equal to EF. Now, this is what I want to focus on here today because that's what we did yesterday, the whole EI equals EF thing. In the absence of friction, in the absence of air resistance, in the absence of any kind of outside force that adds energy to the system, then the total amount of energy at the beginning of the problem will be equal to the energy at the end of the problem and everywhere in between. We left you with the problem yesterday where this kind of comes into play. Here it is. This problem was based on a roller coaster that I went on in Las Vegas about 15 years ago, I guess it was. We had this roller coaster car. It's going at 20 meters per second. It was propelled forward by some kind of electromagnetic propulsion system. Propelled forward, goes, say, 20 meters per second, goes down a little bit of a hill, although not much, and ends up going up this big, steep hill until the track ran out. It stops and then goes through the ride backwards like this. The question that I left you with yesterday was, what's the final height? In other words, how high does this roller coaster car go before it stops and turns around and comes the other way? This might be useful to calculate if you're a roller coaster designer. You're not going to just build the track up and say, yeah, I don't think it's going to get any higher than that. I think we're good there. You're not going to eyeball it. You're going to determine the maximum height that the roller coaster can go, and then you're going to build the track a little bit past that. How do we determine how high the roller coaster goes? Well, we know if we account for everything, then the total amount of energy here is equal to the total amount of energy here, and here, and here, and here, and here, and here, everywhere in between. What we want to focus on is at the beginning and at the end, the initial and the final. At the beginning of the problem, what kind of energy does this roller coaster car have? Kinetic, gravitational potential, elastic potential. Michael, is your hand up? No? Grant, what's what kind of energy it has? Good. It's got gravitational potential because? No. It doesn't have gravitational potential because it's not in motion. Okay? We never define what kind of energy it has based on what it's not doing or what it doesn't have. We always base it on what it does have or what it is doing. Okay? So you're right, it does have gravitational potential energy, but it's not because it's not in motion. In fact, it is in motion, but that's irrelevant for gravitational potential energy. It has gravitational potential energy, Merrick, because it's got a height, right? It's 10 meters above the ground. So we're going to say, yeah, it's got gravitational potential energy. Grant, is there anything else that it has there at the beginning? Any other kind of energy that it has right there? It's got kinetic energy as well. How come, Zach? Yeah. If it's got a height, it's got potential. If it's moving, it's got kinetic. Hey, if it's got a height and it's moving, it's got kinetic and potential. So let's identify here potential. It's got kinetic energy there as well. What about the final energy? Megan, it reaches its highest point. You're on this roller coaster. You see this track ending in front of you. And intellectually, you know that you're not going to crash. But psychologically, you're getting scared right now. The end of the track is coming closer and closer and closer and closer and closer, and then you stop. When you stop at its maximum height, what kind of energy do you have? Potential because you got a height, right? Anything else? Is there anything else when you reach the max height, Dane? Is there kinetic energy when you reach that max height? How come? Oh, wait. It's slowing down as you're approaching the max height. What happens when you reach the max height? You're going up, 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 and then you stop. Right? At the maximum height, you stop and then come back the other way. Is there kinetic energy? Right. Just potential, right? Okay, so we say EI is equal to EF. EI is equal to EF. Potential energy is mgh, and it's also 1/2 mv squared. And final energy is mgh final. We can cancel out the masses here if we want to. We don't need to. Actually, we do need to in this question because we don't know what the mass is. Let's say 9.81 times the initial height of 10 meters. EI was 20. Uh, 98.1 plus 400, 200. The 98.1 plus 200 is 298.1 equals 9.81 times HF. Now we're going to divide 298 divided by 9.81. That's going to give you somewhere around 30-ish, right? 300 divided by 10. 30.387, thank you. Which, how many digits are we going to round that to? Back to our original picture here. 1, 2, 3, 4 digits. Final answer, Kai, should be how many digits? Yeah, final answer should be 2 digits. So we're going to round it to 30 meters. Is that okay? So here's another question for you related to this. Let's say I didn't ask you to calculate the height that it goes to 30 meters above the ground. Let's say I asked you to describe the energy conversions that were taking place here. We start off with potential and kinetic. As it goes down this hill, what's the conversion that's taking place? What's converted to what? Yep. Right. So you have less potential energy as you go down the hill, and you have more kinetic. You had kinetic to start off, but now you got more. You had potential, now you got less. When you reach the bottom here, you've got what? That's right. So all of your potential energy has been converted to kinetic then, and now all you got is kinetic energy, right? Now as it starts going back up this hill, what's the conversion that's taking place now? Yep. Right. Your kinetic energy is being converted to potential until you reach that maximum height, right, Dane? And when you reach that maximum height, what kind of energy do you have? It's all going to be right. Grant, remember that Potential energy is based on height or an elastic or a spring that's stretched or compressed, right? Don't have anything like that here. So it's just based on height. Kinetic energy is based on speed. So at the beginning of the problem, we've got a height, so we've got potential. We've got a speed, so we've got kinetic. But even if at the beginning of this problem it wasn't moving, we would still say we have potential, because the speed is irrelevant for potential energy. The height is the only thing that matters. The speed is only relevant for kinetic energy, right? You guys feel okay with that? All right. We left you last week with a practice test to prepare you a little bit for tomorrow's unit test. I'd like to take a look at that practice test now. We got 7 questions on there. We'll go over 1, 2, 3, 4, 5, 6, or even all 7 questions if we need to. Okay, questions you guys just asked me to go over: 1, 2, 3, 5, 6, 7. Basically everything except number 4. Number 1 says calculate the force of friction acting on an 1,800 kilogram car if the driver brings the car from 100 kilometers per hour to rest over a distance of 40 meters. Hey, notice what I just did? Picked up my red pen. How come? Why did I pick up the red pen, Hugh? What am I going to highlight? There's one thing that I really want to draw attention to here. Yep. Yeah, it's the kilometers per hour. Right, I want to write down all my givens, but I want to draw special attention to that. A lot of people will be able to solve this question, know exactly what they're doing, but make a silly mistake, a careless mistake in using kilometers per hour. We don't ever want to be in kilometers per hour for questions like this. Unless it's a simple V equals D over T question, then don't be in kilometers per hour. Want to be in meters per second. Let's write down our givens here. We're going to say that we got a mass of 1,800 kilograms here. We get a VI of 100 kilometers per hour, which we want to convert that to meters per second because we circled it in red. How do you do that conversion? Nick? All right, that's the cheater shortcut. I didn't teach you that, did I? No, you just figured that one out, or somebody else told you? Oh, in Science 10. Oh, your Science 10 teacher taught you the cheater shortcut. Okay? Yeah, it is. Yeah, it is. Did you guys hear what Nick just said? He said divide by 3.6, and you know what, Nick? That always works. Always. Every single time. The reason that, I do that. I teach that in Physics 30, divide by 3.6. But I don't do it in Physics 20, and here's the reason. I want you to be able to do the conversion in Physics 20, because there's lots of conversions that we're going to have to be able to do down the road. And if I just give you a number, divide by 3.6, you're never going to be able to figure out how to do it, right? That's why we go through that process in Physics 20 of actually converting it the real conversion way, not the shortcut way. Okay? There's nothing wrong with that, just that it might harm you later on when we have to do some other conversion. So what's the way that I taught you how to do this? We got to convert kilometers to meters. How do you convert kilometers to meters? Times it by 1,000. So it becomes 100 times 1,000 meters. Kilometers are gone. How many seconds in an hour? Right. So we convert kilometers to meters, and we convert hours to seconds. We end up multiplying by 1,000, dividing by 3,600, which has the effect of dividing by 3.6. We do that math, it's 27.7778 meters per second. Displacement is 40 meters, 40.0 meters, and we want to find the force of friction here. Anything else we have? If I read between the lines, is there anything else that I have here? Yep. Good. VF is equal to 0 meters per second. Comes to a stop, right? It comes to rest. All right. Here's what a lot of you guys wanted to do on Friday when you were working on this. As I was walking around looking at what you were doing, you said F is equal to mu times Fn. Is that valid? Is that a valid thing to try here? Absolutely it is. Absolutely that's a valid thing to try. The only problem with it is, I don't know what F is. That's what I'm trying to find. But I also don't know what mu is. So although it's a perfectly valid thing to try, I don't think it's going to help me. Don't be afraid to try something if it's valid. Worst case scenario, this. We look at it, we don't have enough givens, we got to find something else. Let's try this. F is equal to m times a. That's valid, right? There's only one force acting, it's friction. When we find this force, it's going to be the frictional force. The mass is 1,800 kilograms, but we don't know what A is here, so we got to find that. Any ideas? Somebody's got to have an idea for this. Jonathan? Yeah, that's exactly what I did. VF squared is equal to VI squared plus 2AD. Rearrange it to solve for A. VF is 0, right? 0 minus VI squared equals 2AD. Take the 2 and the D over by dividing. Okay, you do that math, and it's going to work out to be for A, negative 9.6451 meters per second squared, which we plug into here. And we solve for the force. Works out to be negative 1.74 times 10 to the 4 newtons. It's a big force. That's a big force. But remember, two things. A, we're slowing down this car at 9.6 meters per second squared. So basically, you're going to feel 1 G as you're slowing down the car. The other thing is, it takes a lot of force to slow down a car at any rate, let alone 9.6 meters per second squared. So of course, the number we get is going to be a big value. Take a look at number 2 now. We get a 2.3 bag of candy, 2.3 kilogram bag of candy pulled to the west with a force of 12 newtons. We'll call that F1. And we're pulling it at 30 degrees south of east with 15 newtons. We'll call that F2. I don't like funny angles, so I get rid of it. Let's go over here. Here's my X, here's my Y, here's my 30 degrees. And F2 has a value of 12 newtons. Let's replace, let's figure out what X is. Cosine 30 degrees is equal to adjacent over hypotenuse. X ends up being equal to 12.99. And sine 30 degrees is equal to opposite over hypotenuse. Get 6 newtons. No, that's not right. That's not 12, is it? What should that be? 15, right? So that works out to be 7.5 newtons then, right? Now, if we want to, we don't have to. We've talked about this before, though. We can replace this with 12.99 newtons over this way and 7.5 newtons down this way. And then we can do our X's and Y's. Negative 12 newtons, 0. 12.99, negative 7.5. What do we do once we have those two values? And that's the easy part. And now it's the easy part. What do we do now? Let's redraw it, right? 0.99 to the right, 7.5 downwards. And this is what we want to solve for right here. This angle and this force right there. Find force by using Caitlin the birthday girl. Find force by using you're going to say it. I know you are. Sorry. Find either the angle or yeah, Pythagorean theorem, right? A squared plus B squared equals C squared. I don't care if you remember what it's called as long as you can do it. And theta, of course, we're going to find by the inverse tan function. All right? We good there? Do I have to show you that? No? Question 3. This one says, the coefficient of kinetic friction acting between the bottom of a 10 kilogram box and the floor is 0.30. If the box is pulled to the right by a force of 75 newtons, determine the acceleration of the box. So let's draw this one out. We got a box right here. Its mass is 10 kilograms. We got a force of gravity acting down, and we got a normal force acting up. They'll cancel. We're pulling it to the right with a force of 75 newtons. I'm going to call that FA. And we got a force of friction acting this way. We got to figure out what its value is. What's mu times the normal force? So it's going to be 0.30 times 10 times 9.81. That's 29.43 newtons. Now this question is just like, well, it's even easier than question number 4. You guys didn't ask me to go over number 4. Okay? If you can do number 4, then you can definitely do this at this point, because all we got to do is say F net is equal to FF plus FA. 10 times A is equal to negative 29.43 plus 75 newtons. A works out to be 4.56. Okay, let's take a look at number 5 now. It says, calculate the work done on a 1,500 kilogram car, starting it from rest to 30. The force is used to accelerate the car is 3,000 newtons. What's the distance? All right, let's say mass is 1,500 kilograms. Let's say VI is 0 because it starts at rest. And let's say VF is 30 meters per second. Say F is 3,000. I want to find delta D here. I want to find W. All right, what do you want to do? Here's what somebody in the other class said. Somebody in the other class said, well, we want to find work. Let's say F times D. And I said, yeah, but we don't know what D is. Like, how do we multiply F? We got F, right? But how do we multiply it by D when we don't know what D is? And the person said, well, let's find D. Exactly, let's find it. They said, well, here's what that person did. VF squared is equal to VI squared plus 2AD. They rearranged this to solve for D. It becomes VF squared minus VI squared over 2A. Now, when you do that, okay, you get a displacement that ends up being 225 meters. You plug that in, multiply it by the force, and you get the work done. That's not what I did. Okay, that's not what I did. That's not at all what I did. But yet it's perfectly correct. It's just as good as the way that I did it. Okay? All I did right here is went with something a student was thinking. Okay? That's what I want you to do. Just have a thought, go with it. As long as it's valid, go with the thought. If it happens not to be my thought, that's okay. Here's what I did. How do you find what? How do you find D like this? Is it the rearranging that you're... oh, sorry, you do need the acceleration there as well. Yeah, and you can find the acceleration by saying F is equal to m times A. Yeah. No, good point, good point. Good? Still not the way I did it, but it's just as good as the way that I did it. Here's what I did. I said W is equal to delta E. The work energy theorem. I said W is equal to, well, let's see, we're accelerating it from rest to 30. It's kinetic energy at the end of the problem. It's nothing at the beginning. I just multiplied 1/2 mvf squared and got W. (900 times 1,500 times a half). What is it on? 675,000 joules, which we rounded to 3 digits here. 6.75 times 10 to the 5. joules. All right, good. There's the work. And then, look, once we got work, let's say W is equal to F times D to find displacement. All right, 675,000 divided by 3,000 newtons gives me, and I do have this calculated, 225 meters. Next question. Question 6. This is a hill problem. You know we're going to have one of these on the test, right? One of these inclined planes. Here's our hill. It's at 30 degrees. Go figure. It seems to always be at 30 degrees. We got a box on the hill, and it's 30 kilograms. We've got force of gravity acting down. It's m times g. We've got a normal force acting this way. And we've got F parallel. That's the normal force and gravity combined that actually pulls it down the hill. We know that this angle is 30 degrees. We know that this is 90. Let's get F parallel. Hey, by the way, which way is friction going to act? Slides down the hill, friction is going to act on. Yeah, friction is going to act up the hill. It's going to be smaller than F parallel, right? Let's get F parallel. Let's say sine 30 degrees is equal to opposite of our hypotenuse. Opposite is F parallel. Which 147.15 newtons. Which now it's easy, right? Now it's just F net is equal to the sum of the forces, what we did so many times in this unit, although it's been a little while. 30 times A is equal to negative 147.15 plus 32 newtons. When we solve for A here, it's -3.84, negative 3.84 meters per second squared. Right? Good? All right, we also had a request for number 7, but I'm going to give you a few minutes here. We got some time, so I'm going to give you a few minutes to take a look at that one yourself. Once you're done that, we'll go at it as a class. But since it's so new, we just want to get that feedback from you guys right away here, whether you know it or not. Time to have a look at this one now. It says the first hill on the Mindbender roller coaster in West Edmonton Mall is 50 meters high. If a 1,000 kilogram roller coaster car, including the mass of the passengers, is moving at 5 meters per second when at the top of the hill, how fast is the car moving when it reaches the bottom of the hill? At the top of this, what kind of energy we got? Phil? You got potential, good. It's moving, right? Or sorry, it's got a height, so it's got potential. Just gave away the other one, Phil. What kind of energy, what other kind of energy do we have? Because it's moving, right? And at the bottom, what kind do we have? At the end, what kind do we have? Tom? How come? Because it's moving, right? Do we have potential at the bottom? Zach? No, because it doesn't have a height, right? All right, let's say EI is equal to EF. Let's say MGH initial is plus 1/2 MVI initial, right? Because it's got kinetic energy before it goes is equal to 1/2 MVF final squared. Can we cancel out the mass here, even though there's only one of them on the right side and two of them on the left side? Can we do that? Curtis? Yeah, we can. Sure, it's in every term. We don't need to cancel it because we've got the mass of 1,000 kilograms, but we can, and it makes life a little bit easier if we do. HI is 50 meters plus 1/2 of 5 squared What do we got here? 50 times 9.81 is 490.5 plus 12.5. Is that 503? I'm going to square root that, and it's going to be about, I'm going to say 33-ish, 32-ish, 31.7. We're going to round that to how many digits? It is 3 digits, isn't it? 31.7 meters per second. How many people got that? Good. Now, this is no more straightforward than the question that you'll see on your test. On your test, who knows? Maybe I try to throw a little bit of a wrench into it by doing this kind of, oh, there's a crazy loop in between. Oh, we're going all around there, and so on. But in the end, how does all that crazy stuff change this question? It doesn't. It doesn't matter what path it takes to get there. Okay, if it starts at 5 meters per second, 50 meters above the ground, and it ends on the ground, it doesn't matter how it got there. Nick? That's a good question. Most times it's safe to ignore friction. If there was friction, I would tell you there was friction. Now, in a question like this, where it's not a straight line path, friction would be very difficult to deal with. Okay, so friction, here's the deal. Friction will appear for you guys in Physics 20 only when the object is on a straight line path, not when it's some kind of roller coaster problem or something like that. If in doubt, hey, if it doesn't say anything about friction, just assume that there isn't. It's okay, by the way, on a test too, to put up your hand and say, hey, it doesn't say anything about friction. Can I assume there is no friction? And I'll say, yeah, you can assume that. Okay, I want to give you a short outline here, and it's about 3:07. I think we've got time to do this. This is going to show you that, hey, really, we haven't done as much as you think. We started off the unit a long time ago by defining a force. We defined a force as a push or a pull. And then we talked about the effects of a force. Of course, a force can accelerate an object, which is speed up or slow down an object. It can change direction. It can cause an object to start or stop. But it can also deform the object. So accelerate the object, deform the object. Then we talked about Newton's first law. And along with Newton's first law, we had inertia. Inertia, remember, the tendency of an object to keep doing what it's doing depends only upon mass. Okay, Newton's first law is the law of inertia. An object wants to keep doing what it's doing. An object at rest wants to stay at rest. An object in motion wants to stay in motion in a straight line at a constant speed until acted upon by an unbalanced force. And we had Newton's second law. And for the first time, we saw calculations. Calculations started off with just F is equal to M times A. We had one of these on our practice test, right? One force. It was friction on the test. Could be anything. Okay, one force, F is equal to M times A. Now, you may need to find A by using one of those group B equations. VF squared is equal to VI squared plus 2AD, and A is equal to delta V over delta T, and so on. Hey, look, if you got more than one force, you can't just say F is equal to M times A, but if you've got one force, F equals MA, and if you need to, use one or more of the group B equations. Along with Newton's second law, we defined a normal force, calculated the normal force a whole bunch of times, and most times, the normal force was equal to gravity. So they cancel. And every once in a while, gravity was bigger. Every once in a while, the normal force was bigger. And then sometimes we had one like this, where the normal force acted like this, gravity acted like this, and then we wanted to combine them to get an F parallel. So be able to deal with a normal force in all four situations, okay? Flat horizontal surface, this is usually what we see. Inclined plane, this is usually what we see. We could see this where? When could the normal force be smaller than gravity? Yep. Yeah, like one of those wagon questions, right? Where you're pulling up and to the left or to the right, and you're kind of helping the normal force out, so normal force doesn't have to be quite as strong. Could also happen in an elevator question, right, where normal force is less than gravity. Okay. The only place I could figure this happening, normal force is greater, would be one of those elevator problems. We should be able to deal with all four of those situations when normal force is the same as gravity, less than gravity, more than gravity, and not countering gravity at all. Talked about friction, the two types. You have to be able to calculate that. Right? F is equal to mu times the normal force for both static and kinetic. Know when it's static, know when it's kinetic. And then finally, we talked about multi-force problems. And that could be just like, look, you got a force to the right of 20 newtons, a force to the left of 10. What's the acceleration? Or it could be something like an elevator problem. Could be a pulley problem. Could be one of those hill problems. Or it could be some kind of combination of those. Remember that really challenging question that Sam got right? Got a Slurpee for today? Where you had the hill and the pulley and the elevator and the projectile motion. It won't be like that. Won't be nearly that bad, but the same kind of idea, right? A combination of things. Okay, the most I'll combine here would be two things. Okay, maybe I'll put I don't know, a pulley in a hill, but I won't put an elevator into it as well. Two things maybe. Yeah. No, there won't be projectile motion on this test. Final exam, sure, but not on this test. Then we talked about internal forces. And by an internal force, we mean, somebody was asking about that earlier on. You got a couple of objects here. Maybe this guy's pulled to the right with a certain force. This guy's pulled to the left with a certain force. We want to know what the force is in between. Nick, was that you asking about that? Remember what to do for that, right? Get the acceleration of the system, treat it as one, get the acceleration for the system, and that's just the same as, that's an easy question actually, right? Get the acceleration of the system is just say F net is equal to FB plus FA. Solve for acceleration. And then once you have that, pick one object to analyze and find the force in between. And then finally we talked about energy. And going along with energy was kinetic energy, gravitational potential energy, and elastic potential energy / spring potential energy. Talked about work, talked about power, and then yesterday, finally, we talked about conservation of energy. Spent a lot of time going over this unit, and you look at the outline here, it's not actually all that bad. It's not all that long. Okay, I want you to go home tonight. I want you to review this stuff. Go back and look at your notes. Understand things, internalize things. Don't just try to remember Newton's first law. Understand Newton's first law. Okay, don't just memorize the steps of a problem. Like, understand the steps of a problem. Rework your practice test. Do sample problems. And you should be good to go. It shouldn't be all that crazy of a night for you. It shouldn't be a 4-hour night for you studying for this test. Hopefully, you're in pretty good shape already.